All right, we're going to take a look at radical expressions. We've touched on radicals the very first day of class. We talked about square roots in particular. We talked about perfect square roots, like when we had square root of 25. And we talked about estimating a value when it was not perfect, like, oh, it's square root of 30. Well, that's between square root of 25 and square root of 36, so it's between 5 and 6. That's where we've so far gotten to when we've talked about radicals. So we're just going to expand on that today. So to start with, we're going to remind ourselves that when we have perfect radicals, right, perfect square roots, like 25, we simply know that the square root of 25 is 5. But what happens if it's not a perfect square root and we're not trying to estimate? Like square root 50. What do I do with square root 50? So we're going to address that issue today. What do I do with square root 50 when I'm working on simplifying, cleaning things up, and not approximating? Okay, so I'm not trying to get an estimate. I'm not trying to say it's between two values. What do I do? Well, the first thing to recognize is that it won't be a decimal. And there's a really good reason for that. It's because anytime you would do this with a decimal, it would only be an approximation. We're not interested today in approximations. Approximations are great. It's just not our topic for today, okay? So it won't be a decimal. And the reason that that's the case is because these particular decimal approximations and so forth are trying to represent irrational numbers. I'm going to have an irrational number. I have an irrational number, which is why I can only at best estimate if I switch it into decimal notation. Okay? So what do I do if I'm not going to use decimals? All right, well, let me show you. So we're going to start with that square root 50 that I mentioned already. What am I going to do with square root 50? Well, we're going to factor it. Okay? Factor trees, we've already kind of talked about them briefly. We've also talked about doing a factor ladder. I don't care whether you use trees or ladders. It doesn't even matter to me whether you even show the factoring out. But at somewhere along the way, you've got to show me what the factors are. So if I use a factor ladder, it looks like this. 50 divided by 2, trying to divide only by prime numbers, would be 25. And then 25 would be 5 times 5. If you want to do a factor tree, it's going to look probably, you're going to do the same thing. You're going to do 25 and 2. And 25 is going to be 5 and 5. So no matter which of these ways you do it, you end up with 2 5s and a 2. Is everybody okay with that part so far? So my square root of 50 is going to be rewritten for the moment as square root of 2 times 5 times 5, in whatever order you like. It doesn't matter. Because this is a square root, which we talked about before, and we'll hit on that fact here in just a moment again, we're looking for things that show up underneath the radical 2 times, because it's a square root. So what value shows up underneath this particular radical twice? The 5. Okay, so the square root of 5 times 5 is really the same as the square root of 25, right? And what is the square root of 25? Well, it's 5. So you know, the long and short of it is that if you see 2 items underneath the radical, you can pull it out from under the radical 1 time. Because the square root of 5 times 5 is the square root of 25. And the square root of 25 is 5. Right? 2 5s underneath the radical are the same thing as 1 5 on the outside of the radical. Okay? But it's not just 5. There's still a 2 that's underneath the radical. So this is 5. Square root 2. That's our answer. Now, I want to show you the why, even though I haven't verified for you that I'm allowed to do what I'm about to do. I think you've probably seen it before, and I'll verify that I'm allowed to do it in a moment. But the reason that this is the answer, you know, the why, I asked on the last screen, why? So far I've shown you the how. How do we do it? The question is why. Why is this the answer? Well, why is the square root of 25 equal to 5? Well, it's because 5 times 5 equals 25. That's why. When I multiply the number by itself, I get what's underneath the radical. That's why. So it works the same way here. If I have 5 square root of 2 and I multiply it by 5 square root of 2, again, I haven't verified for you that this is appropriate, but just trust me for the moment. 5 times 5 is 25, and the square root of 2 times the square root of 2 is the same as the square root of 4. And what's the square root of 4? 2. And what's 25 times 2? 50. Case in point, it's the exact number that was underneath the radical to start with. So that's the reason why, and I'll verify for you later that I'm allowed to just do that. So with that sort of under our belt, we're going to take a look at a couple more examples. One more in particular that's just dealing with numbers, 48. So I'd like for you to do either a factor tree or a factor ladder for the number 48. Break it down into all of its prime numbers. So for instance, maybe you start with looking and saying, oh look, it's divisible by 4, and you do 4 and 12. Or maybe you start on a factor ladder and you say, oh look, it's even. I can divide it by 2 and now I have 24, okay? And then keep going until you have all the primes when you're done. If you do it right, you should end up with a lot of 2s and 3s. Like 2s and 3s is what you should end up with when you factor this one down. So let me model the factor tree for you because that's the way I like to do it. If you like the, not tree, the factor ladder, if you like the tree, that's fine. I can divide 48 by 2. I can divide 24 by 2 to give me 12. 12 by 2 to give me 6, and 6 by 2 to give me 3, and then I'm done. So either way you do this, you should end up with 4 2s. Did everybody end up with 4 2s? Good. And 1 3. These are square roots, so I'm pairing these up 2 at a time. And there happen to be 2 pairs of 2s, right? So again, 2 underneath comes out as 1. So this is 2. This one also comes out times 2. But then the 3 remains underneath because his pair was not there. It wasn't another 3. And what is 2 times 2? 4. So this is 4 square root of 3. Okay? Now, number 3, very similar, but I've got a variable with it now. So let me deal with the number part first because it looks just like what we did before. I'll do a factor tree on this one. Tell me, how does 45 factor? Give me one pair of factors. 5 and 9. Fabulous. 5 and 9. 5's prime, 9 isn't. So what will 9 be? 3 times 3. Lovely. So I can rewrite this as 5 times 3 times 3. And there are 4 x's, right? I'm grouping in 2, so tell me a group of 2 that you see. The 3's. What else? Yeah, the 2 sets of x's. Very good. Does everybody see the 2 sets of x's there? So the 3 will come out as 3. And each pair of x's will come out as x. So I have 3xx. But there's still a 5 underneath the radical. What would be a more condensed way to write 3xx? 3x squared. And then square root 5. All right, let's do the 12. I already did part of the 12 a minute ago. 12 is what? Tell me a factoring for it. 4 and 3. 3's prime. 4 would be 2 and 2. So on this one, I have 2 times 2 times 3. And then I have 3 y's. What pairs do you see? 2's and 1 set of y's, right? So there's 1 pair of 2's, so the 2 comes out. There's 1 pair of y's, so the y comes out. What is left under the radical? A 3 and a y. So sometimes we're left with numbers, sometimes we're left with variables, sometimes we're left with both underneath the radical. All of those are possibilities. And we will pick up on this one next time.